Hello, my name is Ramis Khalil, and this is my Lab 1 on constant velocity. Here is a quick overview of what we will be discussing. So the purpose of this lab is to observe the position of an object traveling at constant velocity and compare it with the expected positions that we calculated via computational model. Spoiler alert, in our experiment, we found that Newton's second law is supported. And fundamental physics principles that we will be applying is Newton's first law and Newton's second law. So Newton's first law states an object at rest will remain at rest unless acted upon by an outside force. Basically constant velocity. The velocity of an object is not going to change unless some force acts upon it. Newton's second law states that the force of an object is equal to its mass times its acceleration, which using this law we can infer that objects that are more massive will require more force to move. Here are our models that we use. We use the position update formula, the velocity update formula, and the average velocity update formula. Average velocity formula, which will be used for calculating our initial conditions later on. But in the meantime, position update and velocity update will be used in our while loop, in our glow script computational model. So in our experiment, we took a cart and we rolled it just straight across the ground. We had a meter stick as an axis of reference and to give tracker a distance to calibrate off of. The system here is the rolling cart, and the surroundings are basically the world acting upon that cart. So friction, air resistance, normal force. For tracking the position, like I said earlier, we use tracker. Our predicted positions were calculated using glow script for a computational model, and then all the results were put on an Excel spreadsheet. So here's our procedure. We recorded the cart rolling in a straight line. We put the video into tracker, and then we tracked the positions across a certain time interval. Then we used the computational model as a template. We plugged in all of our relevant values and ran the simulation. And then we took all of the outputted position values and also put them into an Excel spreadsheet where our tracker position values were. So for tracker, this is the first two positions. So we started at a time of 4.27 for our interval, and here we are to 4.3. So our time interval here is 0.03 because that's 4.3 minus 4.27. Our initial position is this value right here that we are going to plug into our computational model, and our initial velocity is going to be this value minus this value over the time interval. So it'll be 0.029 minus it'll be 0, 0. Here's the decimal, ignore the decimal right here, minus 0.00134 over 0.03. And that'll give us a value of 0.318. which is right here, that we plug in for our initial velocity that we just calculated. And that initial position that we just found as well goes right here. We couldn't weigh the cart, so we just set its mass equal to 1. And our clock starts at 4.2 because the interval we go from is 4.2 to 5.8 for our values. And our delta t is 1/30th because frame rate's 30 FPS. So 1 divided by 30 would be our delta t. Here, this is where we apply, I just wrote over it, but this is where we apply our velocity update formula. And then using that new velocity, we do the position update formula to find the new position. And then we obviously increment delta t. Here's the output from our glow script. We're about to put all these into one graph compared to our our experimental results. And here they are. As you can see, they are very similar. They trend in the same direction, but there is a slight difference between actual and expected that can be attributed to some possible errors like friction or air resistance that wasn't accounted for, and maybe some tracker error. It's a software or tracker error because it's a software I'm not super familiar with, so I could have operated it incorrectly or operated it in a suboptimal manner, which could have skewed my data. So here's our what if. What if the axes were flipped? The slope would be negative, but our position versus time would stay constant. and all of our values would stay the same because the signs would cancel. Can we tell what forces are being added together for net force to equal 0? It's very hard to say how many different forces are acting upon the cart. All we know is that the forces add to 0 because the cart's velocity stays constant. Conclusion, Newton's second law is supported because our actual and expected results were very similar, and we can assume there was a constant velocity with 0 net force. And that is it. Thank you for watching.